This is searching for gravitational waves from magnetar bursts. So, yeah, I'll just quickly discuss. Oh, okay. I'll just go through detectors and detections that we know just as a little bit of background, then discuss magnetars. And this talk will focus on essentially the data analysis side of searching for them. And then I will, discuss past searches and the future search outlook. So in the past, we've searched for gravitational waves from magnetars from the LIGO detectors, both the Hanford and Livingston observatories. And in the latest search that we're doing, we're adding in the Virgo detector. So, and in the future, hopefully we will have detections that include the other detectors, Kagra, and in the further future, LIGO India. So just so far, we've detected gravitational waves from binary neutron stars, binary black holes, and even neutron star black hole mergers. Oh, I see. That's the share. Got it. So, so far we've seen in the release data anyways, about 50 different detections. And you can see as the sensitivity increases, the rate of detections increase, so the sensitivity to the signals increases. And we've been through the first 3 observation runs so far. There was a magnetar search in 2002, and then we're working on one in 2003. And then in the future, where in 2004 we will hopefully be at the design sensitivity of a LIGO, and further into the future, increased sensitivity and LIGO India joining as well. The LVK, rather, I should update that too, consists in general of these different search groups. We've heard there's been, the detections so far have been in the compact binary coalescences. And then there's also the continuous wave group looking for things like gravitational waves from rotating neutron stars. Then there's the stochastic group looking for a stochastic background. And then there's the burst group, including things like supernovae, cosmic streams, gamma ray bursts, as well as magnetars. So magnetars were first discovered in 1979. There were observations of repeated bursts of soft gamma rays and hard X-rays from the same location in the sky. Shortly after, there was the first observations of an anomalous X-ray pulsar. So this was an X-ray pulsar that didn't have a partner object to accrete from. In about 1992, the magnetar model was put forth as an explanation for the soft gamma repeaters. And then in 1996, it was proposed that they were also what would cause the anomalous X-ray pulsars. And this was, the anomalous X-ray pulsars were later shown to also emit X-ray bursts, just short bursts similar to soft gamma repeaters. And then there was a second giant flare in 1998. The first was in 1979. In 2004, there was a more energetic giant flare, often termed the hyperflare. So this had saturated the X-ray and gamma ray detectors, and the peak was measured by the onboard particle detectors, which were supposed to be shielded against the most energetic solar flares from the sun. And then there was also these higher frequency oscillations known as QPOs that were observed in the tails of the giant flare. In the tail of the giant flare. There's been some recent observations showing that magnetars share features with high magnetic field pulsars, and some magnetars have been observed to give off radio emissions. And then in April of 2020, a galactic magnetar was observed to give off a fast radio burst. So that was pretty recent. So what are magnetars? Magnetars are neutron stars with very strong magnetic fields thought to be on order about 10 to the 14 to 10 to the 15 Gauss. They're the model for the SGRs and AXPs. And they're observed to give off intermittent bursts of hard X-rays and soft gamma rays. There's these short bursts they give off with energies up to about 10 to the 42 ergs. And then there's rare giant flares with energies up to 10 to the 44. And in the case of the hyperflare, estimated to be around 10 to the 46 ergs. So there's been 3 of those seen of the giant flares so far in maybe almost 40 years now, actually, I guess. So they're much rarer than the short bursts. And then the short bursts have been seen down to the lower limit of the X-ray sensitivity. And there's about 30 magnetars that we think there are. 24 have been confirmed as either SGRs or AXPs, and then there's 6 additional candidate objects. So the mechanisms of bursts, the main ones that are thought to be are crust cracking and magnetic reconnection. So with crust cracking, there's been simulations that suggest it could be up to, of the neutron star crust breaking strain, that suggests they could release energies up to 10 to the 44, 10 to the 46 ergs. And then with the crust cracking, the idea is that tension builds up in the crust from perhaps drifting magnetic fields, and then the crust reaches a certain point where it causes a star quake, and then you get the crust cracking and causing a short burst. And then with magnetic reconnection, when magnetic field lines reconnect, it emits a burst. And it's thought that these are behind the giant flares, and they can occur with or without crust cracking. So a few additional characteristics of the magnetars are that they are observed to give off continuous X-ray emissions. About a third of them give off continuous optical emissions, and there's more thermal energy than expected from just the hot core. So it's thought that the magnetic field might be heating up the crust. And then there's also stages known as outbursts, where there's increased quiescent emission, as well as the bursts tend to be, there tend to be more bursts and more energetic bursts, and a period of outbursts was observed before the 2004 hyperflare. There's also glitches and anti-glitches that have been observed. So a glitch is when the crust of the star gets slowed down from magnetic braking, essentially, and if the interior of the star is still going faster, then there'll be a glitch where the crust speeds up. And then an anti-glitch is where it suddenly slows down in speed. And then finally, there's been radio emissions observed from magnetars. Specifically, there's been the fast radio burst that was observed in April 28th of 2020. And you can see here data from CHIME of, in the spectrograms here, of the 2 close together peaks from the FRB. And it's a little anomalous in that usually the FRBs go down in frequency when they have a pair like this, but this one goes up. But this was also detected in coincidence with an X-ray burst from the magnetar. Now, the X-ray burst was just a short burst, and we've had much more energetic bursts like the giant flare and the hyperflare. So from previous observations, non-detection of FRBs from other bursts actually means one of 3 things needs to be true about FRBs, which is 1, they wouldn't be emitted with every short burst, or 2, perhaps they are beamed, or 3, perhaps the fluence ratio between the FRB and the X-ray burst can vary quite a bit. So another interesting thing is magnetars have been thought to be a potential source for FRBs for quite some time. Population estimates of magnetars throughout the universe suggest that they could potentially be the source for at least quite a bit. They could explain most or perhaps even all of the FRBs that have been observed, but if they explain the more energetic FRBs, then it would need to be something like an energetic giant flare, or perhaps the more energetic FRBs would need an entirely different source for them.
What's the difference between the 2 plots?
Sorry, what?
What's the difference between the 2 plots?
Oh, the 2 plots? Okay, so I'll have to look at the paper again, but I believe that this was from CHIME, and I think this might have been, yeah, I'll have to look that up. I think this might have been from the other, there was also the STARE-2 detector that detected them. But I'm not sure if that's from that or a different detector entirely. There were a few different detectors that detected the FRB. So considering magnetars as a gravitational wave source, it would be a targeted search, since the location of the magnetars is known from electromagnetic observations, and then we also get the time to search. Being a neutron star, they're a compact object. And their distances are relatively close, ranging from about 1.6 kiloparsecs to about 62.4. And there's many around the 10 kiloparsec distance. Then it's thought that bursts could potentially excite non-radial modes, such as F modes, R modes, and alpha modes. And then if these were excited, they might emit gravitational waves, which is what we're looking for. Okay. So quick summary of past searches. The first search was actually on the 2004 giant flare targeting the higher frequency quasiperiodic oscillations. Then there was searches for gravitational waves associated with F modes after that. The stacking burst search was interesting. There was a period where there was sort of what they call a burst storm. So there was a lot of bursts in a short amount of time from the same object. So then they took the data from the different bursts and they stacked them together to increase the sensitivity. And there was the search during S5, and there was also a search on what is thought to be an extragalactic giant flare from a magnetar. Then there have been a couple long-duration transient gravitational wave searches, and those are the ones that I've been involved in, specifically the one in S6, and there was also one in O2, and we're working on one now as well. So how do these searches work? So you can see on the right here, actually, we have a graph from the 2004 giant flare. And so you have the initial peak on the left there from the initial burst, and then there's the tail afterwards. And so with the tail, when you have the magnetic reconduction, a certain amount of that is trapped as a fireball in the magnetic field, and then that rotates around the star, and that's what's thought to give the modulations you can see in the plot here. Then in addition to that, in the tail, there was observed higher frequency oscillations, and those are the horizontal lines here, ranging from about 18 hertz to about just under 2400 hertz.
What's the vertical, and is that EM or gravitational?
Oh, the counts, that's EM, yeah, electromagnetic. Yeah, exactly. Okay, so there are two basic searches we're doing, basically a short duration and a long duration search. The short duration is essentially targeting the F modes because if they're rung up, they're thought to disappear quickly, so it'll be very short duration. And for this, we're using a software known as XPipeline, which looks at the data coherently between detector pairs. And we're looking for both a small window just around the burst, looking for initial F modes there, and then a longer window afterwards in case the F modes are rung up perhaps from some interactions with the core. It's an unmodeled search. And then the long duration search uses a pipeline known as STAMP that's written in MATLAB, and essentially the idea here is motivated from electromagnetic observations of the QPOs, just looking for long duration signals that don't change much in frequency. And there's many QPOs that have been observed to occur in frequencies LIGO is sensitive to. Okay, so for the long duration search, we calculate frequency and time maps that use a detection statistic, and the detection statistic is on the top left there. It's a cross power between the two detector pairs. So the two S's in the top are the Fourier transforms of the data in each of the detectors, and those are normalized by the auto power. And then we have an unpolarized filter function that we use, which is the Q factor there. Basically, it adjusts for the phase difference between the gravitational waves coming in each detector, and then each one of these points is calculated with that method. And so once we have the time frequency map, we calculate different clusters searching for the signal. And so the clusters are just the S and R's added together of every pixel in the cluster, and then divided by the square root of the total number of clusters. Yeah?
Sorry, maybe I'm missing it, but so that's comparing the two gravitational wave detectors. But do you do a search with the gravitational waves correlated with EM measurements?
So what we're using EM measurements are two things. One is the time we're looking at, and one is also the direction in the sky. So it narrows it down to where we're looking And so what the time difference is between the data when we put it together, and also when we're looking at the data stream. Does that answer your question? Yeah.
I guess, but not like a direct correlation.
Not a direct correlation, no, yeah.
Because that wouldn't be useful, or it seems like you'd want to maximize what you know from EMs.
Right, so if you have something like a giant flare, and that was done in the first search, there was the information of the QPOs was used directly to look for excess power in those frequencies. But a lot of the bursts we don't, some of the bursts there have been some tails, but a lot of the bursts we don't necessarily have as much information to look at. So you would just have the initial peak, essentially. And so at least for the long duration, we don't have any of the information on the QPO specifically that we'd look for. So we just do a general search, basically.
Okay, so do you get like a lower threshold for detection in terms of SNR then, based on that? Or it's still like SNR of 8 or something like that?
Lower threshold, what do you mean?
Well, so like with binary neutron stars and stuff, if you had like an EM counterpart or something, then in principle maybe you wouldn't require so much SNR to know.
Oh, I see. Right. So, well, the threshold is essentially determined from the background of exactly what we're looking for. So, yeah, there hasn't been a specific threshold set, but that's determined by essentially, you know, depending upon how many sigma you're looking for, essentially, if that kind of addresses it. So, yeah. Yeah. Yeah, it's an unmodeled search, yes. This one is unmodeled. So yes, if we had models or something like that, that would, you know, change things, and you'd be able to.
Well, yes. I mean, I hate to monopolize here, but I mean, with the QPOs, you've got like characteristic frequencies from the EM, right? And then you might expect like maybe a doubling for the gravitational wave frequencies. Then.
If you can observe the QPOs, yeah. And then, but there's also questions of whether the QPOs directly, you know, line up with the gravitational waves due to the complications of the magnetohydrodynamics and whatever the interaction is causing the oscillation to be visible electromagnetically, essentially. So it could be quite close, which would be nice, of course.
So you're not using that?
I'm not using that, no. This is just completely unmodeled, so yeah. So. Also, yeah, like I said, we don't always have the QPOs, or often rather even, to observe from either. If we did that, that would be nice. Yeah. Right, so, okay, the unmodeled search that we're doing is basically just using what are known as seedless clusters. So with the short duration search, we use seeded clusters, where in that case we're looking for building these clusters from the top, the highest 1% of the pixels as seeds, and then building clusters from that. But with the long duration search, you can see there's these bands, these black bands across here. So depending upon if there's different frequencies or time periods that are noisy, we'll want to cut those. And so if we have a long signal that goes across them, a seedless cluster is useful to be able to pick that out. And for this, we use these quadratic Bezier curves you can see on the bottom. So basically picking out 3 points and building a monotonic curve from that. And just talking about cutting frequencies. So for example, in S6, you can see in this ASD here, there's different frequencies that if we didn't cut would drown out any signal that we would see otherwise in those frequencies, since we're looking for a loudest cluster search. So we cut out 60 hertz harmonics and calibration lines, for example, in violin modes. And then just a note about the polarization function. So there was some work that was done in the O2 search looking at what the cross power would be in the imaginary and real components. So you can imagine if you use different filter functions, you'd pick out different parts of these boomerangs, essentially. So different parts of the sky have a different potential shape in this phase space here. And so since we use an unpolarized filter function, we essentially take the real line of this. And if we did any additional, if you did multiple filter functions, for example, each time we would run it, that would both potentially increase the background as well as increase the computational cost. So we used unpolarized filter function, which gets a lot of the potential signal there could be. And then really quickly, in terms of the background, so when we have a trigger, we pick out a time and on-source window around the trigger, and then the time outside of that on-source window will be used to build a background. And for the long-duration search, we end up taking periods of time for the cross power from different windows in the background and time shifting them together to build the background. So for building the background distribution, we use on order of about 1,000 time-shifted background pairs. And then we calculate the false alarm probability, which is just the number of clusters. So from each one of those windows, we get a single loudest cluster, which is what we use from each window. And then we calculate the number of clusters in the background that are at or above a given SNR and divide that by the total number. And from there, we can create this background distribution and use that to estimate the false alarm probability of the on-source trigger. So it's not a particular SNR we're looking for, but rather we're trying to characterize it by the false alarm probability. Okay, so once we get that, then for example, in this example, we looked at the on-source event and it was well within the background. So nothing, no signal in this case. This is S6. Yeah, so this was an older one. Yeah, in 02, there was 4 triggers, and all of them were actually pretty low in the background as well, near the lower end. So in the case of no detection, then we would look for upper limits to exclude potential gravitational waves that might be there. So again, if we had waveforms, specific waveforms to model, we could inject those and test those, but what we're using are half-sine Gaussian and sine exponential for the long duration, and for the short duration, what's been used is white noise bursts, ring downs, and chirplets. So on the top right here, you can see just as we vary the strain, the SNRs recovered will change, and so we define the detection efficiency by the number of injections that have an SNR greater than the on-source SNR. And so from this, you can see we did this variation for different waveforms to get the values of the strain and the gravitational wave energy for different waveforms. Okay. So just a quick note on the computational challenges from the data analysis side. So with each one of these windows, we end up with a time frequency map with nearly 2 million pixels, and then each one of these, we calculate about 30 million clusters using the Bezier curves. And so then question is how long does this take? In an earlier talk, I think in the workshops, it was discussed using GPUs for some analysis versus CPUs. And we could see here, in an earlier version, there was a GPU version that was working, and this took about 15 minutes per window. With the hardware and MATLAB changing, now it only runs on CPUs, and now it takes usually between about 1.3 and 3 hours, but it can range up to about 12 hours. So it's at least about 5 times longer. So, you know, the gains from GPUs are nice. Building up a significant background takes a lot of time. The current search is going to take a little over 1,000 of these background sections, and they take about a day to run if everything goes smoothly. So, yeah. Then how might we reduce the time for analysis? There's a new version being developed in Python for this. One of the things they do, so we are calculating on the data after it's put into the cross power, the different clusters. And one of the things that's done in a different clustering algorithm, slightly different, which will be the standard for the Python version, is they actually calculate the loudest clusters before putting the data together. So that reduces the amount of time for the search significantly. Also, GPU options with Python, such as QP, might be added to speed up the clustering, and some work I did with TensorFlow in the past suggested that it could be useful in speeding things up as well. So, and it might also, since we're using, you know, a bunch of different random numbers to generate these clusters, Perhaps, if we use a specific seeds, we could parallelize finding the clusters even further to speed it up as well. So this is an open problem, essentially, to speed up the search.
TensorFlow, that's neural nets? So.
It does do neural nets, but it's been a while since I looked into exactly using it, but I believe it doesn't just need to be used for that. It's just processing numbers, essentially. So if you tell it what to process, it gets that set up. And there were ways where it was used with the GPU, which was pretty simple, to, programmatically. I mean, like, it wasn't difficult to do that, but it seems just that TensorFlow is set up to efficiently work with the GPUs. But it's been a while since I looked at it. TensorFlow seemed faster significantly. I think some of the other things, QP would probably need some work because it took a lot of time to just load all the numbers in. Once the numbers were in, then it was very fast, but loading the numbers in was almost as slow as the CPU when I was looking at it before. So, yeah. Okay, so what have we seen so far then for magnetars? Well, we haven't detected anything, which is probably obvious. But we have set upper limits for the different searches. So on the 2000 flare giant search, where they focused on a different QPOs, the best upper limit was just below 100 hertz, 92.5, and it was about 8 times 10 to the 46 ergs. For S6 and the best upper limit was about 10 to the 46 ergs, and then for O2, it was about 3.4 times 10 to the 44 ergs. And you can see on the top right here of this plot, the S6 results are the light triangles, and then the darker triangles are the O2. So we got about an order of magnitude improvement in strain from one to the other. And so now these energy levels are comparable to giant flare energies for these frequencies and these injections. The electromagnetic burst energies were much smaller at about 7 times 10 to the 39 ergs and 10 to the 36 ergs for S6 and O2 respectively. So the giant flare was about 10 to the 46 ergs. So any ratio you would get between the electromagnetic and the gravitational wave energies was much more restricted from, say, a giant flare event than we would get from a normal burst. But it would be interesting if we got a giant flare. So basically, the LIGO can currently probe burst emission mechanism energy budgets for a giant flare at this point, depending upon the sky position, of course. And then just quickly discussing, we get a strain upper limit, of course, but what we think of this in terms of is the energy upper limits, and this depends upon the distance to the source. So for O2, the distance was just under 9 kiloparsecs, and about 10 kiloparsecs is a common distance for magnetars. So if you get closer, then the upper limits will be stricter in the energy of the gravitational waves. So it'll be, if we got a really close giant flare, then obviously that would be very interesting. Okay, so what about now? Well, right now we're looking at a search for O3. And for O3, we have 13 magnetar bursts that we're analyzing. And 6 are from just the LIGO detectors. And then with Virgo, we're adding 7 additional ones. This includes a magnetar that was discovered in 2020. And it also includes the magnetar that emitted the fast radio burst. So this is the first time either of these objects has been searched for gravitational waves. 2 of the bursts are from the new magnetar, and then their energies are up to about 10 to the 36 ergs. And then the remaining bursts are from the magnetar that emitted the FRB, and the energy, at least one, is up to 10 to the 38 ergs. And simulations estimate, at least one simulation paper estimates that, with a simple simulation, estimates with the energy of 10 to the 44 ergs, you could maybe get an F mode with a gravitational wave energy of 10 to the 36 ergs. So it's unlikely from this that with the burst we have that we'll be seeing an F mode. But it also suggests that if lower frequency modes last longer, on order of 100 seconds, they may reach energies that could be detectable by a LIGO or future detectors like the Einstein telescope for giant flares. So what sensitivity, what upper limits might we see in the near future? Looking at two different waveforms, low frequency one at 150 hertz and then a higher frequency around 1500 hertz for the F modes, we can use O2 as a comparison, assuming a similar SNR, and then a similar sky position in terms of the antenna responses. We can scale from the O2 to O3 and O4. So for O4, I'm just using the LIGO design curve. So that gets to, for the low frequencies, 2 times 10 to the 44 or even 10 to the 44 ergs. So that gets it down into the giant flare energy range. And then for the F modes, it's 10 to the 47 or 3 times 10 to the 46 ergs, which is the order of down to the order of magnitude of the hyperflare for O4. In the future, there will hopefully be some third-generation detectors, the Einstein telescope in Europe and Cosmic Explorer in the US, and Cosmic Explorer potentially having a 40-kilometer baseline, or long arms, rather. If we estimate for these, I use this plot here just to do a quick estimation. We might get, for the low frequency, up to down to 10 to the 44 or even an order of 10 to the 41 ergs. So this puts it into the energy range of the more energetic of the short bursts. And then for F modes, we're getting into the energy range of the more common, or, well, 2 versus 1 out of 3. So the lower energy range of the giant flares that we've seen. So in summary, magnetars are a potentially interesting candidate to search for gravitational waves. We're looking at 13 for O3, and the sensitivity should increase as the gravitational wave detector sensitivities increase, and the current sensitivity should be comparable to the electromagnetic energies observed in the giant flares, depending upon the sky position. Yeah, thanks.